Okay, so this chapter talks about various kinds of components that put other mechanical components together. One is, of course, the screw. And the key for the screw design is to understand what's happening inside the thread. Okay? And there are some terminologies that we need to know. So there's a helical geometry, as it's called the thread. And it's a periodic geometry following this helical curve. And since it's made in a periodic geometry, so you will see the same shape of the thread next to each other. So you can actually compute for the pitch. So pitch is a key dimension for thread. Just like when you are designing for a gear, you have periodic geometry, so you sometimes care about the distance between the exact same shape. So that's basically pitch. Okay, and there are two diameters. One is the root. The diameter at the root is called the minor diameter, and there's another one at like the tip. The English is called the crest, okay? Like the top of the mountain. Okay, so that diameter is the major diameter, and at the middle there is a pitch diameter, just like how we study the gear tooth. So it's like we imagine most of the load will be concentrated at specific position, and it's like right at the middle of the thread. So usually the pitch diameter is at the average of the minor and the major diameters, like at the middle. So for later on, when we study for the forces, we assume the forces are concentrated at the point, right at the pitch diameter. But in reality, the entire face of this thread is carrying the load. It's a distributed load. And so it's a assumption that the forces are concentrated at one point. Okay? And usually at the edge there's a chamfer. Okay? And also the way how the thread has this angular opening is called the thread angle. And in this, over here, it's defining half of the opening as the thread angle. So half of it, from center line to the other side, this opening equals to alpha. So the total opening equals to 2 alpha. Okay? So there are various kinds of shapes for the thread. This is like a general geometry. You don't need to know too much. So basically, you can look for the detailed dimensions from the category. So if you go by the thread, you can study all the values right there, and you need to find the one that matches to the bolt. Okay. So please be aware that in the category, it shows one dimension is called the stress area, tensile stress area. So it computes for the area. So what does the area mean? It's like an effective area. So it's like if you if you want to know how much tensile force that you can apply to lengthen the thread, it will let you know, okay, the stress area, you should use this number, okay? So it's not the area computed from any diameter. So this is I think they use experiments to estimate this stress area. Okay. So this is another different series, different categories. So like this one is in the inch units. Okay. Also, you can see tensile stress area. Okay. This is another kind, like a square shaped, and there is a tilted slope kind. So the category tells you how the geometry looks like. Okay. That's the number. Usually, this kind of square thread will be utilized for holding to provide strong lifting. Okay, usually that's it. Because it will allow. Because if you have like a triangular thread, the force between the thread and the bolt is gonna be perpendicular to the contact surface, which is along certain angle. So that means you will have a axial component of the force and the radial component of the force. Okay, so it's like some part of the force is not completely along the axial direction. If you have some thread and if you try to push something up, if there's a weight, you try to rotate the thread and then push this like a jack. You want to push this up, right? Then what are holding the weight? Basically, the thread right here that is holding the weight. So there would be a weight for the thread itself. Basically, there's a W, and you will be having a lot of reaction forces pushing up at the surface of the thread. And since your thread is, if you're having a triangular shape, then your force, the supporting force comes this way. So there will be if this is a center line, you will have a horizontal component and a vertical component. So only the vertical component is helping you to lift the thread, the bolt, to hold the weight. Okay? So if you can have like a square shaped thread, then all the forces between the threads could be utilized for holding the weight. Okay? So that's why there will be different purpose for threads. So like this is a power thread. This is you have a like a worm gear on the right side. This is like a worm gear to lift this screw and to lift something up. Like there are various applications, and they use rectangular threads. Okay. So here is the basically analysis. Here it is. So as I mentioned earlier, there are some force coming up, coming from the top. Okay, and you have some, well, either it's a nut or it's some structure, and the whole system has to carry the load. Okay, so it's like if you view the screw and the structure together as a system, and you have to have some direction forces. Okay, but what's inside, what's between the screw and the nut basically would be the force reactions happening at the surface of the thread. So if you have never studied the force reacting at the surface of the thread, you may not easily understand what's going on right here. So let me explain to you. So imagine the surface, the tilted surface of the thread is following some kind of helical curve. Okay? So if I take a walk, for example, from here, I will be going up and then like this, right? I didn't draw it correctly. It's gonna be like going up, yep, up to the same position, right? Yep. If you view it from the side, it's like a sine function. But it's like you are taking this helical curve. Okay, and let's take a walk along the pitch diameter. So I should make it even more accurately. This is the major diameter, and the smallest one is the minor diameter. So there's a diameter that is at the middle. Okay? So that would be the pitch diameter. So let's stay on top of the pitch diameter and then start to do the walking. So it would be like something like this. Okay? If you start from left hand side and you take a walk and then goes to the same point. And that's a helical curve. Helical curve. So can we unwrap that trajectory, that helical trajectory, unwrap it and make it a line? It's like you are climbing, you are walking up toward some kind of hill, but originally you are taking the walk and then making the turn, following some kind of helical curve. But now there's a straighten the going uphill as a linear uphill. You're going up. Then you are in this particular drawing. So this drawing is representing the climbing uphill of your walk along the helical curve. Okay, so that's why right here the horizontal length, total length, would be the diameter of one, like a one, not diameter, the perimeter about the center with the diameter of pitch diameter. So this one is pitch diameter. Okay? And then this would be your pitch, because you are going uphill and then following this helical curve, your movement up would be one pitch. So that would be your pitch. So then you know how this geometry is going to look like. Okay? And so let's say all the forces are concentrated at one particular point. So you can then analyze what would be the reactive forces. So, first of all, you will have some normal force, and you will have a friction force. So now you need to figure out why the friction force sometimes goes downward, sometimes goes upward. So it really depends on whether you are trying to lift the object or drop the object. So if you are lifting the object by pushing up, then you are, this is your thread, and this would be part of the nut, right? So it's like if you are lifting the thread up, then relatively you are like moving this way. So this is your moving direction. You're like moving the thread along this interface. So if you're moving this way, then your friction should be following the direction that is against you. So your friction force would be going down if you are lifting. So this would be, I think this is a lifting case. Okay? Because you are moving up, so your friction force goes down. Okay? And what would be the force that lifts your thread up? Usually it's based on some kind of torque that rotates the screw. Okay? So PR basically would be the like a transverse force that generates this torque. Okay, so this would be the force going that allows this rotation, and that force that you generate definitely is going around the center. So in this particular drawing, you see following the horizontal direction. So that's why you have this force balance right at certain point along this hill. Now for dropping, if the friction is strong enough, your object may not be too heavy, then this power screw can hold its own position due to the friction force. It will be holding it. You don't, unless you have very smoothly surface and or you have some like a lubricant oil right in the middle, so your friction becomes very small. So that power screw may be dropping to the bottom if you are not holding it, or maybe the weight will push it down by itself. So it really depends on how much friction force you have. Sometimes the power screw can stay there by its own friction force. Okay? So if you would like to push the object down, you need to spin this screw the other way to allow this thread to go down, right? So when that is happening, your thread is moving down, so the friction from the nut actually pushes the thread up. That's why the friction force is having an opposite direction compared to the lifting condition. And since you are pushing, you are trying to make the direction the opposite direction, so this is coming down. So this transverse pushing force would be coming from the right to the left. So that's why this is the force that you for the push. Okay? I think I explained both cases reversely. This is for raising. R represent raising. So L represent lower. So in that case, this drawing is the this would be the nut side, and this is the thread. Is it? No, hold on. Oh yeah, I'm doing it right. What happened? I'm doing it right. Raising, so lifting. Yes. I explained everything correctly. So I was right. Sorry. Yep. Okay. So that's the force balance. So what you need to do next, basically, is to study for the balance. You can then determine what's the required force to push the object up, based on the solution for force balance. Okay, and inside the equations, you will see coefficients of the friction coefficient, and also the tilting angle. Okay, and this is how much weight. So what's affecting the required force? How much weight you are pushing up? What's the incline angle of your thread? How much friction force you have between the thread and nut? So that defines how much force that is required to push the object up or to push the object down. Okay, that would be that's the result of force balance. Okay, and you can also use it to compute for required torque if you are using some kind of motor to drive it. So you can use it to compute for what's the required torque. So you can then determine what the motor you're going to use. Okay. So what is self-locking? Self-locking is what would be the required friction between the thread and the knot so it doesn't drop its height as you release your hand. So it's like you don't have any pushing forces to lower the thread, but you still want the friction to hold the weight. So that's called the self-locking. So there will be a condition. The friction, at the end, the friction coefficient has to be strong enough so that it will satisfy the self-locking condition. So no matter what's the position of the screw, it stays there. The friction force holds the entire screw right there. And of course, this analysis doesn't count the own weight of the screw. So if you are trying to hold the screw, including its own weight, you need to consider the weight of the screw as the external force as well. Okay, so over there when you have the value of F, if you want to consider the weight, then the weight should be included inside F. Okay? So that's an idea of self-locking. Okay, so the other part I would like to talk about is failure. This is an important drawing. So the other kind is the screw and bolt, the screw and nut for you to tighten things together. So think about what you usually do for tightening the screw. What's happening is, as you spin the screw, this basically tries to move up and this tries to move down. The screw tries to move down, the nut tries to move up. So with these movements, you actually provide some kind of clamping. So it's like a clamping force. Okay? And on the other hand, when you try to clamp whatever that's at the middle, for the bolt itself, it actually is being lengthened. As you try to move, tightening the screw, the bolt is going to be lengthened. Basically, there will be a tensile force at the middle. Okay? So this is how you can truly have a good clamp of the object in the middle. So you see, it says the bolt stretches because it's being lengthened. And the material property of the bolt, the thread, the screw, is trying to recover its own shape. So it's like a spring force. It's trying to recover, and that force is gonna clamp it, gonna clamp the plate at the middle. Okay, so you need to understand when you tighten the screw, you actually stretch the bolt. Okay, so right here, there is one way to analyze what's happening inside. So let me remind myself what is K1. KB is bolt. So this one is bolt. Okay? And T and D represent T is the thread. And D would be the rod. T is the rod. So So the idea is that you are treating the entire bolt as two portions, and a part is having a thread, the other part has no thread. Okay, and due to the geometry, that if you take a look at the cross section, the thread part and the rod part, this part is the rod, and this part is the thread, right? So geometrically they are different, and their length is different, the stress area is different. Even though they are having the same material, so their Young's modulus is the same, but the cross section area is different. For the rod is simpler because it's like a cylinder. So the area of the cylinder is gonna be the area of the rod. But like I said earlier, if you are considering some kind of thread, how do you know what's the area for the thread? So over here, this is the stress area. And that can be provided from the catalogue. It tells you, okay, if you're using this kind of thread, then the stress area should be certain value. And here is the length of the thread, and here is the length of the rod, right there, okay? So when you are treating both parts as springs with different properties, what's the total property of the entire spring? They are being placed in a series, so the spring coefficient is like calculate is not directly summation. It's a summation with the inverse. Okay, when we inverse, then you can sum together. So with this, by this equation, you can then get how to compute the overall spring coefficient. That's why at the end, the spring coefficient K of the bolt, the entire bolt, equals to the last equation. So basically, you're treating the rod part and the thread part as two different springs, and they have different properties. Okay? Once you have this, what do we do next? This is telling you what's the usual length. But care more about the strength of it. This book doesn't analyze. Okay, so at least from here you can study I don't want to go to this one. So that's one way for you to know how to compute for the overall spring coefficient. But this one is more. I don't want to go through this one. Okay. This is about the car right here. So over here you can actually see why you need the spring coefficient, because the force inside the bolt allows produce some deflection inside the bolt. Okay, and it's gonna depend on how much spring coefficient you have. So basically, it's treated like a spring. So your force equals to K times delta. Okay? So you can actually compute for how much displacement you have. Okay? And you can do the same thing for the this is for the whole part. Okay? And is let's see, else for members in grip being compressed. Okay, so if you now you are starting like this. Once you already know the spring coefficient of the bolt, now you're starting in this way. This object is being clamped, right? And your bolt looks like this. And this is your nut, right? And right here, this is your bolt with the coefficient KB. So originally, without this clamping, it has its original length. Now, when you try to tighten it, so it will be lengthened certain delta. So the amount of the lengthening equals to delta. And on the other side, for the members, so these are called the members in grip. So these are the members. Since the bolt is being stretched by delta, that means the members is being compressed by delta as well. So same amount of the delta, same amount of the displacement, but for the bolt is being stretched, but for the member is being compressed. And they are all within the linear elasticity range. So the F equals to K times delta X is still valid. Then you can figure out, okay, there are some forces inside you can then use it to compute for the relationship between the force inside the bolt and the force inside the member. And since due to the same amount of the deflection, these two equations can be combined together. Okay. So what's next? Okay, anyway. So usually you will apply certain force to have a initial grip. Okay, and right here is trying to use the equation. Let's see. The total force equals to the force inside the bolt plus the force inside the member. Okay, so you can then end up with the second equation. So you need to, from the previous slide, you know, the force inside the member equals to PB over KB times KM. So it can be, you can end up with this equation. The force inside the bolt would be equals like this. And the force inside the member equals like this. And there's a coefficient C. Stiffness constant. It depends on the spring coefficient inside the bolt and spring coefficient inside the member. Okay, so there's a table telling you different different sizes of the bolt, for different bolts. Basically, you can have different spring coefficients, okay, and it computes for the C value. Okay, so it's easier once you have the C value. It's easier for you to understand what would be the force component inside the bolt from your external force, and then the rest of the component would be the force inside the member. Okay, so right here, this will be the total force that tries to break the member, and the total force that tries to break this assembly basically is going to be held by the force inside the bolt and also force inside the member. Okay? The thread is being lengthened, is trying to recover back. The member is being compressed, is trying to recover back. So that force is inside, is going to support the reaction forces to balance with the external forces. Okay? So that's the idea. This I don't want to go too detail. I think this is what I want to tell you about the bolts. You can similarly you can use it to study for fatigue. Like this is what we have learned for fatigue, right? You can then use it to study for basically same equation. Okay, you can now for all kinds of mechanical components, as long as you can study for the stress, then if it's carrying fluctuating loads, then there's a fatigue issue. So when it's about fatigue, then what we have learned in the past can be utilized. Okay. So right here, I don't want to go through the details. It's basically the same equations. Then you can compute for the safety factor. Okay. This is basically examples of different fatigue models. Okay. This is a different failure modes. They are some details I'm not going to cover. So that's everything I want to cover for the bolt. And let me see what else I haven't covered yet. This is welding we talked about last time. I think I haven't talked about spring. I think I can quickly go through talk about spring. So when we are studying the force inside a spring, you need to know how the spring looks like. Spring is basically a circular wire. Basically a wire with circular cross-section, but being wrapped into a helical shape. Okay? So it's interesting that before this lecture, you probably don't know. When we stretch the spring, do you know what kind of force that is applied inside the spring wire? Actually, it's torsion. So if you think about it, if you try to either compress it or pull it, and if you pay attention to everywhere inside the spring, the angle of the helical curve either becomes smaller or larger. So pay attention to that particular point. Actually, that small area is being twisted. So if you pay attention to some area here, when you try to compress it, then it's being twisted in one particular way. And if you try to stretch it, then it's being rotated, like a squeezed in the other way. So actually, there will be a stress of torsion. So it actually is it's going to be a shearing stress due to torsion. Okay? And let's say you are trying to compress the spring, and you still also still pay attention to somewhere inside the spring material. That pushing force is gonna shear everywhere inside the spring, and it's gonna be a shearing force up and down along this cross section. So there's also shearing stress. So this is coming, the direction is up and down, and the torsion basically is following the direction of the squeezing. So every time you compress a spring or pull the spring, everywhere inside this helical wire is carrying shearing forces, shearing stresses in different ways. So you will need to compute for the total shearing stress. So it's like you can sum them up, okay? But it's not that accurate, because when you pay attention to some small area, it's not a straight, it's not a lying horizontal shape, it's not a lying cylindrical shape. It doesn't lie on the floor. It's not completely flat. It's being, it's like having some certain angle. Okay, and also your spring is being twisted in a very nonlinear way. So this part, the torsion part, comes with a correction fact, like a coefficient. Okay, coefficient, and it's being experimented and realize how much correction that is needed. So you can then compute for the more accurate shearing stress inside the spring. If you know the stress, then you can make sure it's within the safety range. Okay? So in this particular lecture, actually, we don't compute for k equals to k delta x. We actually care about the material inside. Okay? So let me show you the equations. Like I mentioned earlier, this is the torsion part, and this is the shearing part. Okay, and you can just treat them as a cylindrical geometry lying down. So the A is gonna be the circular area. F is gonna be the force, and J is gonna be the polar moment or inertia for circles. R is the small radius of the wire, and torque is gonna be how much torque that is generated, and it can be computed by the force couple, right? So it's going to be F times half of the big D. So this is from the center point here to here. That's capitalized D. And this is small r. So half of it is big D over 2. So the distance between a force couple generate this torque, and there will be a torsion right here to balance. So that's how you compute for the torque. Okay? So with all these parameters plugging into the top equation, you end up with something like this, but that's not the end. You can then realize there are some common terms. If you if you put some terms together, it ends up with something like this. And if you define something called C, it's called the spring index, defined as big D over small d, then this term can be rewritten as that term can be rewritten as 1 plus 1 over 2c, right? So it's basically this. It's a 2c and 2c plus 1. So this K, this is basically the K shear stress factor, right? But there are different models of this shear stress factor. This 2c plus 1 over 2c is one model you can use. Right here, there's not yet being updated, but there are different models right here. These are the models to update the coefficient that I just mentioned, because they realize if you directly use 2c plus 1 over 2c, it's not accurate enough. So there are researchers trying to figure out like this Well and this Bert Strausser, they did some research and realized you can correct the K value in certain way. Okay, so they are based on different research. So if you correct it, then you will have more accurate, more realistic estimation of the shear stress inside the spring. Basically, they update this K coefficient. Okay. And also from here, there is a common equation that can be derived. And as you can see right here, they use it. You can even estimate the spring coefficient of a spring when you manufacture a spring. So this equation has been memorized by many students if you are trying to take a national exam in Taiwan. Students usually just memorize it. As for whenever there is a national exam about mechanical design, if it's about this chapter, if the exam is about some other part, it's too difficult. But this is a part that's commonly seen in the national exam. So anyway, if you're interested, if you know the diameter of the wire, basically this is a small d, right, as mentioned here. If you know the shear module of the material, if you know the big D, basically the diameter from the center to the center, big D, okay, and if you know number of the coils, so one pitch is like a one coil, and another one are two coils. So number of coils. So n is the number of coils. So with these numbers, you can estimate, this is the spring coefficient K. So if you know this, F is going to be equals to this particular K times delta X. So before this lecture, maybe you have never seen this equation before, or you have seen it. But how is this being calculated? Basically, you can see it's based on the stress analysis that was derived earlier. But I'm not going to go through all that. So you can, if you want to memorize anything for the spring chapter, I think this equation is one equation for your memory. Okay? Or always check the textbook. For example, if you try to produce your own spring in certain shape, as long as it's a circular cross section, and if you coil the spring properly, and if you know the shear modulus, if you know how, you can, of course, you know number of coils, you know the diameter and also the diameter of the wire, you can estimate the spring coefficient. You can make your own spring with certain values of the spring coefficient. Okay? So actually, that's what I want to let you know about the spring chapter. Okay? So I think I cover another component as well. Chapter 11 is bearing. I think I don't have enough time for bearing today. Next time I can try tomorrow. Tomorrow I can talk about the bearing. Okay? Chapter 12 is about lubricant. So I think I will talk about the ball bearing. There are some statistical models for ball bearing, and chapter 13 should be the gear. So we already covered the gear. 16 will be clutch and brake. We haven't talked about clutch and brake. 17 is pulley. We haven't talked about pulley yet. There's no more. So we haven't talked about pulley and belt and ball bearing. And what's the other? Ball bearing. Clutch and brake. So after, in the following lectures, I will talk about these. Then I cover only the kind of touch have a small touch of every component for you to know about some common knowledge of the design of each kind of components. But if in the future you are truly designing for that particular kind of component, you may need to study for more information, because there's many detailed research inside those components. And I would like to go to the our syllabus and take a look at the schedule. So we have, today is 2nd. So tomorrow would be, the last chance for me to talk about mechanical components. If I miss any of it, then we just miss it. So next week, I'm not here. So next week, Dr. Patel will be having discussion with you. And then on the 2 weeks from now, we will have final presentation. Okay. and we don't have class on the 17th. So I know 2 students wants to do the makeup exam. I haven't give the makeup exam yet. I will create the exam sheet soon. So maybe this week or next week you can complete your makeup exam. Okay. Any questions? Okay. Okay. Playing games. How's the game? It's okay. It's your own decision. Okay. That's it for today. Please make sure you do your homework. So for your final presentation, I will need Word document, also your final presentation, and if you have any other kinds of files, including videos, whatever, simulation files, or other files, you will please submit them to me. So on the day you present, of course you will hand in the PowerPoint. And I will give you 1 more week for the rest of the file. So maybe you try to polish the document or you try to finalize it. On the day of the final week, you have your presentation done. And a week later, that will be the deadline for the rest of the file. So overall, the scoring of the final project includes your overall performance and also all the documents that is being prepared. So that's it. How I judge for your final project. Okay? Any question? Okay. See you tomorrow.